Let's keep talking about tolerances. Why do you think designers give you a tolerance versus just a target dimension? If you, for example, see a blueprint with dimensions on it, it's not going to say produce this part to exactly 2 inches. It's going to say something like produce this part to 2 inches plus minus a thousandth of an inch. So there will be, in this case, a 2,000th of an inch tolerance. Gives you some elbow room. Why do you think designers bother to do that? Wouldn't it be better to just machine everything exactly to 2 inches without variation on either side? Well, that's impossible to do. We're going to experience variation in whatever we do. It occurs naturally in processes, for example, heights of people. If you get 30 people in a room, they're going to vary in heights. Most of the people could probably be clustered in the middle 1/3 of the distribution, and then you have few people that are higher and a few people that are shorter. Same with intelligent. There's, in any natural process, no two products or occurrences are exactly alike. You will incur variation. In processes that have to do with manufacturing or service or really anything, variation is typically due to what we call the 6 M's. Those are man, machine, Mother Nature, method, measurement, and materials. Those things will cause variation and we can't get away from it. Now, take a look at this statement. Quality is inversely proportional to variation. What does this imply? It means as one goes up, the other one goes down. If variation goes up, if you have more variation in your processes and systems, your quality will go down. That has direct financial implications for you. Let's take a look at a case. One of the big 3 automotive companies realized that they had some problems with transmissions. When they dug a little bit deeper, they saw that the warranty returns for transmission differed depending on which country the transmissions were produced in. And you know that these days parts for automobiles are manufactured in all kinds of different countries, and then they are shipped to an assembly plant, and then the car is put together. So you can have transmissions that are produced in the United States, you can have transmissions that are produced in Japan, and you can have the car assembled in Mexico. This is what happened here. And they noticed that the transmissions that were produced in Japan had a lot lower warranty costs than the transmissions that were used in the United States. In fact, it was less than 1/3 of the warranty returns for the Japanese transmissions than the United States transmissions. So they dispatched a team to look into that, investigate it. And the first thing they did is they got a whole bunch of transmissions from the US, and they got a whole bunch of transmissions from the Japan, and they took them apart and they measured the dimensions to see whether the parts were produced to specifications. They found that the parts manufactured in the United States were manufactured within specifications, and the parts manufactured in Japan also were manufactured in specification. Now, if you take a look at this picture, the vertical line on the left that says LSL is the lower specification limit, and the line that's on the right that says USL is the upper specification limit. And then those bell-shaped curves in the middle show you the distribution of the parts that were measured. And you can see that the curve for the United States is a lot wider, it's broader, it uses up all the available space between the spec limits. However, parts were made in spec. And then you can see the Japanese curve is a lot narrower. It uses up only about half the allowable tolerance or specification limits. This directly translated into cost of quality. So the less variation you had, which in this case the Japanese company had a lot higher quality, which translated into fewer warranty returns. This case illustrates that we are always striving to reduce variation, to give the customer a more consistent product, a higher quality product. So less variation translates directly into higher quality. A lot of this class is about analyzing how much variation do we have and what does the variation look like, so we can do informed decisions about what to do about the amount of variation. Do we have to act? Do we not have to act? Do we have something extraordinary in our process happening that's causing us variation, or is our variation overall too high, or is our variation satisfactory? So the tools we learn in this class, a lot of them have to do with analyzing variation. Your book talks about the evolution of modern quality philosophies, went through many iterations. Book says it started out with inspection, and a lot of companies are stuck in that particular age of modern quality. Inspection, let's talk about each one in a little more detail. Inspection refers to those activities designed to detect or find non-conformances existing in already completed products or services. So basically what you do, you manufacture a part or you conduct a service, and then after the service is done or after the part is manufactured, you take a look at it to see if it's good or if it's bad. If it's good, you ship it. If it's bad, you do something, either throw it away or rework it. So inspection is controlling quality kind of after the fact. You focus on the product, not the process. You may also refer to figure 1.12 on page 11 in your book. The next stage in modern quality is quality control, so that's a little better than inspection. It refers to the use of specification and inspection of completed parts, subassemblies, and products to design, produce, review, sustain, and improve the quality of a product or service. So quality control goes beyond inspection by making sure you have some standards, ensure that you have conformance to the standards, take action if there's a lack of conformance to standards, and implement plans to prevent future non-conformances. So if you, for example, inspect a part and you find it's bad, you figure out why, and you take corrective action to prevent future non-conformances, and you make sure you have a standard that's very good in the first place. So quality control is a little more in depth than inspection, but you still focus on the product and not the process yet. The next stage is statistical quality control. It involves collecting statistical data, analyzing the data, and interpreting it to solve problems. Statistical process control prevents defects by applying statistical methods to control the processes, making the products or providing the services. So how is that different from just quality control? Well, statistical quality control or process control focuses on the process itself, not the product. So you don't wait until you make bad parts and then look at them and decide what to do with them. No, you look at the process while you're producing parts. In the process, you take data from the process and analyze it to see whether you are stable, whether you're predictable, or whether you have some extraordinary variation or too much variation, and then you take action on that. So it's higher on the evolution of quality because you focus on the process. Let's do a little exercise to illustrate why inspection, like focusing on the product, doesn't really work that well. So let's all pretend we are inspectors. In the following paragraph, it's pink here, treat the letter F, whether it's capitalized or lowercase, as a defective item. So you inspect the paragraph and count the number of defective items. Now read the paragraph. Do it only once. Remember, you have lots of paragraphs to inspect. You do it all day. You're an inspector. Figure out how many F's, non-conforming product, you have in this paragraph. This little presentation will stop right here, and we take up this exercise with the next presentation.